Thank you very much for this kind introduction. This work has been done in the framework of the FIB Task Group 2.1, which deals with serviceability models. And this work is, the title is Assessment of Crack Spacing and Crack Width Formulation in Reinforced Concrete Elements Externally Strengthened with FRP Materials. And the co-authors are Professor Francesca Ceroni from the Partenope of Naples in Italy, and Professor Alejandro Pérez Caldentey from the Politecnica de Madrid in Spain, apart from myself. So the outline of the presentation is a typical outline with an introduction and a review on the theoretical models, but I want to point out in this part that I will go to explain reinforced concrete without FRP strengthening and with FRP strengthening, and that's because the work has been done in the FIB environment. The codes that I'm going to analyze are the Eurocode, the new recently approved Model Code 2020, and the FIB Bulletin 19. Then after that, we will see the experimental database that we could collect, the comparison with the existing results, summary, concluding, and some future works that we are currently developing. So if we go back to the cracking problem that we teach in our classes, and we explain which is the cracking process of a reinforced concrete tie, we all know that there is a non-crack stage. In this non-crack stage, apart from the transfer length, we have full compatibility of strains in all the sections. This means that the strain in the concrete and strain in the steel are the same. Then if we continue increasing the load, eventually the strain in the concrete reaches its maximum value, so there is a crack. In that point, there is a redistribution of shear stresses, and this is the crack formation phase. This effect will be carried out until we cannot develop more cracks. This is called the stabilized cracking phase. No, so if we put this in another shape, we can talk about the tension stiffening effect, which we all also know, that is, the contribution of concrete in between cracks. No? And in this graph, we can see the typical graph of the tensile force in the reinforcement, in this case is steel, depending on the mean strain value. Then if we do another step, we go to the general expression for crack width, and we assume a mechanical model for crack width that is the crack spacing times the mean strain difference between steel and concrete. We can see two terms here. The first one refers to the mean strain value, so we can refer here to the tension stiffening. And the second is the mean distance in between cracks that usually refers to the transfer length. To obtain this transfer length, we can mechanically obtain from equilibrium of forces based on two different things. No, the equilibrium of forces at the height of at the level of the reinforcement, and in between the cracked and the non-slip section. Okay, so then if we do this calculation, we obtain the typical value for the transfer length that I think it's known for all of you. That usually depends on these factors, and what the codes say usually is that then we give a normal value, a normalized value for the tau depending on the FCTM. Now, if we have a look on the Eurocode and the new proposal of the model code, the formulation for the crack width is basically what I have just seen, and there is one term K for the model code that I will introduce later on, and the main assumptions compared to the previous slide are that the equilibrium of forces is done given a constant shear stress along the effective length. Okay, so this is one thing, and the other thing is considering a constant tension stiffening effect. So, Eurocode 2, as I said, the characteristic value for the crack width is the crack spacing times the mean strain difference. Then the maximum crack spacing can be mechanically derived, but in this case, we have two terms. One term that accounts for the effect of concrete cover, that is the first one, and the other term is the one that we can obtain from equilibrium. In this equation, there are several factors, but in fact, they correspond to the previous slide. So the bond properties, usually for steel, we have the good bond properties, so this is 0.1. Then we have the strain distribution factor, and then there are two empirically calibrated factors. Then there is an open discussion regarding which is the effective reinforcement ratio that we should consider. This effective reinforcement ratio depends on the effective height. And in the case of Eurocode 2, it is solved as you can see in the slide. Regarding the second part of the equation, the mean strain difference is based on this equilibrium of forces, assuming the tension stiffening, the constant contribution of tension stiffening that I just mentioned. So if we move to model code 2020, the first thing that we can see is that there is a new factor, that is the effect of curvature, that maybe for the ACI is not new, because it's just considering that the crack width increases linearly from the level of the reinforcement to the bottom of the beam. Then the maximum crack spacing is again the sum of two factors, the effect of the cover and the effect of the shear stress transfer. But in this case, what we find is that for the second part, there is another empirically adjusted parameter that is the one that has into account the casting factor. Okay, so this is new, and the other part that is new is the stress distribution factor. And sorry, and the last one is that the way to calculate the effective area has also changed. For the mean strain difference, there are no differences except for the tension stiffening coefficient. Okay, now we move to FRP strengthened elements. In this case, what we know is that the transfer length can be also calculated the same way, but of course, considering the two reinforcements. In this case, I'm going to evaluate what the FIB Bulletin 90 says. In there, we published two models. One is a mechanical model that assumes that the crack width is 2 times the slip, both at the height of the steel reinforcement and at the height of the FRP, known and a bond-slip relationship. The problem here is that this non-bond-slip relationship depends on many factors, and this gives us an iterative approach. We thought that this was not the straightforward formulation for designers, so we evaluated the second model, that is a simplified approach that is empirically adjusted from Eurocode. So this is the model simplified. You can see here that the maximum crack width, again, has the two factors that we were saying, the factor depending on the cover, that in this case has been fixed, and the second factor that depends on the shear stress transfer, again, but in this case is fully empirically adjusted to a given database that was present in that moment. For the mean strain difference, it's the equation that was in the Eurocode version 204, with the only difference that it has been adjusted for an equivalent effective ratio. So as you can see here, so there is the first factor that is that one of the steel, plus the second factor that is for the FRP. Okay, I must say here that when this formulation was done, it was done for the area for ties was considered 3 times the diameter of the bar. The database that we could collect at that moment is not very big. It has only, as you see, 36 elements in flexure and 31 elements in tensile force. For flexion, we managed to find some elements with wet layup, procured EBR, some procured NSM, and some very few with NSM rods. For ties, all the elements were with wet layup EBR. You can see here the cross sections, the concrete average compressive strength, the steel reinforcement ratio. Okay, I would like only to put some attention on the last row that it says preloaded element. This is something that is still under discussion in the group because we don't have specimens that have been preloaded, and we think that it is interesting to have them. So we didn't have any of the beams in that moment. And how all these elements were measured, we fixed the service load at 80% of the yielding of the steel. And another very important thing is that the shrinkage strain was not reported for any of the tests, so we could not have this value. For the crack measurement, in all the specimens, the crack width was measured at the height of the steel reinforcement at the lateral side. In the beams, we only considered the cracks appearing in the pure bending zone. In the ties, it was all the cracks that appeared. And we tried to collect mean, maximum, and minimum values. Although you will see that in the next slides, we only consider the mean value. Another open issue is how researchers measured the crack width. We found some, of course, in the beginning, the crack width was measured with handheld microscopes, and sometimes it was with LVDTs. Later on, people have used DIC. So this also gives some dispersion of results, as you will see. Okay, the results. I'm going to present for crack spacing and crack width the results in this shape, which is first Eurocode, second model code, and third FIP Bulletin 90. In the vertical axis, we have the theoretical value. In the horizontal, we have the experimental one. So it means if the point is on the part on the top, it's over-predicting. It's on the bottom, below the line, it's under-predicting. So over means safe results, under means not safe results. So first I'm going to talk about crack spacing. For the crack spacing, as you can see, Eurocode and model code, that were two codes that were not thought for strengthened elements, over-predict the results. And this is something that we were expecting because we are not considering the additional reinforcement that is taking place. So this is something that was expected. The formulation that was empirically adjusted in the FIB 90 was giving good results. Okay, this was okay. We didn't know what would happen because we were adding here NSM, and it was not calibrated for NSM. But in general, it was having good results. I might say here that the dispersion of results was extremely high. So, and I forgot here to say you one thing, that is we are only checking here the mean values, because for the maximum values, the dispersion of results was even worse. So we consider the mean values, and for those codes that were calculating the maximum crack spacing, and hence the maximum crack width, we obtained what for each code was the mean value. Okay. For ties, the problem grew, so it became worse, because the dispersion was even bigger, but especially for model code and Eurocode 2, the results were largely overestimated. Our theory is that apart from not considering the additional reinforcement, there is an issue here on which is the area in tension that we should consider. We were considering the full area of the tie, and all the ties have had different dimensions. So this is another open issue that we have here. Sorry, for the FIB, the results were more or less correct. Then let's go for the crack width. In this case, first I'm presenting Eurocode and model code, and you will see that surprisingly the results get better. So if you remember, I'm going to go 2 slides here. We were having 1.3 as a mean value, and now we get around 1 as mean value. What was happening here? According to our theory, is that we have 2 possible explanations for that. The first one is that none of us, because I was also measuring some of the tests, were measuring the shrinkage. And the effect of the shrinkage, what is giving to us is an additional strain. So if the shrinkage that was taking place during the tests was not measured, but was providing a crack width. So in a way, we were doing some tricky things, no? Because we were not considering the shrinkage that was taking place, and because of that, the error that we were having in the crack spacing was compensated. Okay, this was one of the things that we think that was taking place. And the second one is that, the expression for the mean strain difference was not considering the effect of the additional reinforcement. Then if we go for the FIB bulletin, surprisingly, the results here are underestimated. Okay, and we think that, again, the effect of the shrinkage was playing this role. So we had a good adjustment for the crack spacing, a disadjustment for the crack width. If we move to the ties, remember that the ties were largely overestimated. So we have basically the same trend that we saw for the beams. The overestimation becomes a bit smaller, we think, for the same reason. And we don't know what happened with the ties and the case of FIB 90. Well, we have one theory that is that, again, that the tensile area in concrete was playing a role. If you remember here, we were considering the 3 times the diameter, probably was not the case. So we said, okay, let's assess what's happening with the shrinkage, no? And we did a very quick calculation, assuming that we have the stress in the steel, that is for 80% of the yield strength, so we can have the value of the strain, assume a free shrinkage of between 300 and 500, and with that we can have an increase in the measured crack width of around 15 to 25%. This can explain the difference that we were having in the FIB bulletin predictions, and also can kind of explain the jump that we had from the crack spacing to the crack width for the other two. For the case of the ties, we cannot find more explanations. We think that there is something here apart, that is the area intention. So, conclusions. The first conclusion that we think that we have to point out is that we have very few experiments. So concluding like this is not nice, but I think it's what we have. So we aim to increase the database. And the second one is that we had a large scatter of results. As is expected for crack spacing and crack width, but too much maybe. If we check the crack width, we see that in generally is overestimated for the two codes that were not considering the FRP reinforcement, and it is expected, and it was quite okay for the FIB bulletin 90 predictions. For the crack width, it might be more affected by the scatter, even though we try to consider only the mean values. And which are the reasons for that? Well, maybe the accuracy of the instruments, the load levels, the place where we all were measuring the crack width. In some of the cases, it was not reported, some of the cover, and some things were not very well explained. But okay, this is something, but we think that the main issue here is the unknown level of shrinkage that was taking place. For the comparison with the FIB 90, in the beams we had this underestimation of 15%, again because we think about the same. For the ties, we think that we need to work a bit more with the tensile area. And for the Eurocode 2 and model code, well, as I said, the distances between the theoretical values of crack width and experimental ones are lesser because of the two possible reasons that I explained. I think that the first one I explained quite a lot. The second one is that if we consider that the strain in the reinforcement is exactly the same, the tension stiffening contribution changes. So if we are considering the effect of FRP, we would have more strain. So because we were not considering that, we were having less, and this means less crack width. Finally, for the influence of shrinkage, we want to say let you know that, no? Is it reliable to calculate the mechanical models on both experimental values of crack spacing and crack width? Or is it more correct to use only the experimental values of the crack width and use the mechanical model to predict is it more correct to use the experimental values of the crack spacing and use the mechanical models to predict the crack width? For the future works, we need a model that takes into account the contribution of both internal and external reinforcement, and we want to calibrate it with more data. Just to show which are the future works that we are carrying on in the FIB Task Group 2.1, we are proposing a new new transfer length that is based on the same concepts than before, but assuming that we have a new equivalent reinforcement ratio that considers both reinforcements. This means that if we do the equilibrium, we will have to take into account the perimeter in contact between the FRP and the concrete, and of course we will have to have one coefficient for EBR and another for an NSM, and another if we have another kind of perimeter. Then with that, and based on Model Code 2020 approach, we will have the new crack spacing and the new mean strain difference. So I don't know if I went too fast. Thank you very much for your attention.